Hi guys. Today we'll be trying to solve this. Uh, this is from part A. This is question number 7. So it's a question on sequence of functions. It's a pretty nice question. It's an easy question. Uh, so basically it is saying we are given f and x to be 1 by 1 plus x to the power n, and basically they are saying that option A is Fn converges uniformly on 0 to half. So bunch of options on uniform continuity, and the last is Fn converges pointwise on 0 to infinity from on 0, close 0, open infinity, right? And the B and C option is Fn converges uniformly on close 0, open 1, and close 0, close 2. Okay, so let us first try to so let's just say, I mean, looking at the function, the limit function will exist, right? So let us try to figure out the limit function, and then we will try to do the rest. So this will be, so limit n tends to infinity, like this will be, first will be 1, right? For x greater than equals to 0 to less than 1, right? Because yeah, if x is less than 1, x power n is 0 as n tends to infinity, so the denominator will be 1, and so the whole thing will be 1 since the numerator is 1, right? So this is the case. Now this will be, for x equals to 1, we can just put 1, so this will be half, right? So this will be half at x equals to 1. Now right. Now, if x is greater than 1, x to the power n is, as limit n tends to infinity, this will be infinity, right? So the whole thing will be 0. So this will be 0 from x is 1 to uh, 2, right? And we are doing this because, I mean, it's given that, yeah, so and 0 x greater than 2. I mean, we could have written this like, I mean, both together, but yeah, whatever, we can just for the like sake of convenience, we are just writing it like this. Now, so this is our like limit function. So Fn converges pointwise. Yeah, it converges pointwise. It is not uniformly continuous, but yeah, I mean, yeah, it converges pointwise, right? I mean, yeah. So Fn converges pointwise on 0 to infinity. This will be true. Right, because we have a limit function, so it converges pointwise. Yeah, I mean, what I mean to say, it might not be continuous, but I'm sorry, might not be continuous, but it converges pointwise. Now for option C, okay, it is saying that Fn converges uniformly on closed 0 and closed 2. Right. So if Fn is continuous, right? For each and Fnx is continuous function, right? Suppose it converges uniformly on this, then the limit function should also be continuous, right? Okay. But there is a discontinuity at x equals to 1, right? So the limit function is like this. So this 1, this is 0, and at 1 we have this discontinuity. It just suddenly becomes half. It suddenly goes like this, and yeah. So and the rest is 0. So basically, so there's a discontinuity here. There's a jump discontinuity. So this is not continuous. So I mean, we know by a theorem, right, that if Fn converges uniformly, where Fnx is bunch of continuous functions to f, then f should also be continuous, right? But here, if f is not continuous from 0 to 2, yeah, on 0 to 2, so this option is false. Right. Now for option A, okay, option A is pretty nice because it is saying that Fn converges uniformly on 0, on closed 0 and closed half. So basically we need to work with this closed 0 and closed half. Okay, so yeah, we need to work with this closed 0 and closed half. Now one more thing, like if you notice, like this is the function fx is continuous. Okay, the function is fx is continuous. Um, so fx equals to 1. I mean, it's a constant function. So, so this is continuous. So basically, fnx converges pointwise to this, and fnx is also continuous function. It converges pointwise to this continuous function, and this set is compact, right? And this set is compact. So, like, if it is either monotonically decreasing, fnx, or increasing, if like either they are monotonically increasing or decreasing, we can say using Dini's theorem that this will be uniform. This converges, fn converges uniformly to f, right? Okay, so we do not need to check using mn test. We can just directly say that. Okay, so basically we have to check if it's monotone. Now to check this, right? Basically say n is greater than m, right? Then um, x to the power n is less than x to the power m, since we are talking about this interval, right? It's they are less than 1. So this will imply that 1 plus x to the power n is less than 1 plus x to the power m, right? I am not writing for all, for each step, each and every step, but yeah. So this would mean that 1 by 1 plus x to the power n, since we are doing a reciprocal, right? So basically increasing. So increasing on this. Okay. So yeah. So this, they are monotone. So using Dini's theorem. So using Dini's theorem, Dini's theorem, we can say that fnx, I mean fn converges uniformly on f on 0 to half, right? So yeah. So this option is true. We didn't even need to check. In exam, we can do this very fast. So yeah, this is okay. And now option B is saying Fn converges uniformly on 0 to 1, 0, 1. Right. So I mean close 0 and open 1. Right. So basically, yeah. So basically the same function, like if it constant function. So I mean now here we cannot apply Dini's theorem because 0, 1 is not. I mean this is not compact. So this is not compact, right? Not compact. Okay. Now we have to check uniform continuity here. I mean, sorry, uniform convergence here. I'm sorry. Yeah, could be uniform convergence. So, so, right, right. Basically, let's just we can just use this, and we can now use MN test. X belongs to 0, 1, and mod x to the power. Sorry, yeah. I'm sorry. This will be 1 by 1 plus x to the power n minus 1. Right, which is nothing but supremum x belongs to 0, 1. So if we, okay, let me draw a straight line. Yeah, so this will be basically like if we remove the minus, since it is mod, then x to the power n by 1 plus x to the power n. So basically we need to find a supremum mn. Now yeah, now one thing is that, okay, so let me just write gx to be x to the power n by 1 plus x to the power n. Right, now g dash x will be basically n whole square. This will be 1 plus x to the power n, x to the power n minus 1. This will be n minus x to the power n, x to the power n minus 1. Right, so this will give us this two, this one here and this one here. The term will get cut out. So basically, in sorry. Basically n x to the power n minus 1 by 1 plus x to the power n whole square. Now this will be greater than equals to 0. Of course, this is 0 at 0, but this is like if you are not including 0, this is strictly increasing. Right, this is if the g dash x is greater than 0, right? So basically gx is increasing function. So gx is increasing on, yeah, gx is increasing on, so yeah. So gx is increasing on this closed interval 0, 1. Yeah. So because x is greater than 0, right? So if x is greater than 0, g dash x will be greater than 0. So it will attain its supremum. supremum at x equals to 1, right? So basically our mn will be half. So our mn will be 1 by 2. So mn will be half, which implies limit n tends to infinity mn, which is half, which is not equal 0, not uniformly convergent, right? So we are done. This was a pretty easy question, pretty nice. So this is false. So only option A and D are correct. Okay.